we constructed a four-plane graph based on the points in white where the x values from here to here double, from here to here double, from here to here double, and the y values from here to here fourple, from here to here fourple, and from here down to here go down to 1/4, so from here to here they're fourple. Okay, so in the usual manner, we locate our points, we construct the graph, and now we first prove that if x doubles y, we prove that y equals ax squared is a model for this graph. And to do that, we prove that if x doubles, then y does indeed fourple. So to prove that, we let x1 and x2 be two x values with x2 twice as great as x1. And then we take our y1 and y2 values, and looking at the graph, 1, 2, 3, 4, it looks like this just about fourples between here and here. But we're going to prove algebraically that if we constructed the graph correctly so that y it really does fourple when x doubles, that well, we're going to prove that if the graph is y equals ax squared, then when x doubles, when x2 is double x1, then y2 has to be double y1. So y1 is a times x1 squared. If this is the model for the graph, then that must be so. And if and y2 equals ax2 squared. So that our ratio y2 over y1, if the graph really is fourpling, should be 4. That's equal to y2 being ax2 squared and y1 being ax1 squared. We have ax2 squared divided by ax1 squared. The a's could be divided out here, but I wait a step. x2 now being 2 times x1, we can replace x2 with 2x1, and then we do the simplification, and we end up with just 4. So that proves it. Then we assume a point 314 somewhere in the graph. I just picked a point about in the middle, called that 314. Okay, so that x equals 3 is here, and the x graph is then scaled accordingly. And none of this was scaled. We constructed the graph unscaled until we located this point. None of this purple was here. There were no numbers on the graph. Now there are numbers since we have a definite x and y values for definite points. So 3 here, 14 here. And then we conjecture the rest of the scale for the graph based on those two values. So we started with value 3 here, value 14 here, and estimated where the other numbers would go. Having done that, we estimated the coordinates of the point where x equals 2. So for x equals 2, we come up here and over here, and it looked like we got 7. For x equals 5, we're also estimate for 5. We got 5 here. We went up to the graph, came over, and we got 40. Now, we then used the y and x coordinates of this point to determine the value of a. Y is ax squared. That's the assumption. And these points are supposed to be in the graph, so we put this y value in here. We put this x value in here. We get this equation, and I don't have to read the solution to you. It's a very simple equation that's solved for a. We get 14/9, and we conclude then that if this is a y equals ax squared graph and y equals 14 when x equals 3, the model has to be y equals 14/9 x squared. Then for x equals 2, we evaluate the function and compare with the estimate we made here. So we plug in x equals 2 into this model, and we get y equals 4.2. Doesn't agree all that well with the 7 that we estimated, but of course there are flaws in any freehand graph. For x equals 5, the estimate is much closer. We get 38.5, where this is supposed to be 40. Okay? So, the lesson is we got good plausibility for the fact that this is an appropriate model for a four-plane graph. and confirmed by creating the model for a point, any old point on the graph with given coordinates. We get the model, then we plug the x coordinates of our other two estimated points in and see how we did. Not great, but not too badly.